So far, we have learned linear SVM for separable data. For example, for the picture on the left, the two groups of data can be separated by a solid blue line. And there are many such blue lines that can separate the two groups of data points. We wanted to find not a line, but an avenue that can separate the two groups. And we want this avenue to be as wide as possible. And that's related to the concept of margin. We have formulated the max margin problem and in terms of the slope parameter beta and the intercept beta 0. So that's known as the Primal Problem. And it has p+1 arguments or parameters we aim to estimate. And we actually solve the dual problem where the dual problem has n parameters, lambda 1 through lambda n, one for each data point. And they are basically the Lagrangian multiplier from the primal problem. And the two sets of solutions, the solutions for the two type of problems, primal and dual, are linked through the KKT conditions. Meaning once we solve the lambda from lambda n from the dual problem, we can find out a way to solve or retrieve beta and beta 0. And what's interesting about the solution is due to this compatibility condition in the KKT conditions, most of the lambda i's, the Lagrangian multiplier, is going to be 0. And the only, for example, for the data on the left, there are only the two data points on the dashed lines, and they're going to have non-zero lambda i's. And those are the points that are going to play a role in determining beta and beta 0. So from that sense, the SVM is quite sparse. And the data points whose lambda i's is non-zero is called support vectors. So SVM, the machinery is really determined by just a handful of support vectors. In this case, for example, if I move this data point, as long as I'm not going to cross the dash line, then the solution will stay the same. Or if I just delete this one, again, the solution stay the same. So SVM is pretty robust. What if the data are not separable, meaning there does not exist a blue solid line that can separate the two groups of data? For example, for the configuration of the two group of data points on the right, you can find out it's impossible to find a linear line that can separate the two groups. So we're going to talk about how to solve this problem, and there are two possible ways we can generalize those the so-called hard margin formulation to address this non-separable data. One is called soft margin. In the hard margin setup, which is on the left, you can see we place a wide avenue between the two groups, and there's no data points will be allowed on this avenue, and also no data points would be allowed on the wrong side of the dashed lines. Now in soft margin, because the data points are not linear separable, again we're going to place a wide avenue to separate the two groups, but we allow some arrows on the data points. So for example, in this picture, there are two green dots. They are on the wrong side of their dashed line. So eventually, the objective function becomes a linear combination of two terms, and one term reflect the margin which we want it to maximize. Another term reflect the error which we want to minimize. So the final solution is a trade-off, and we wanted to place an avenue as wide as possible, but meanwhile will allow us to make some errors on some data points. Another extension of the hard margin formulation is that, we cannot, for the picture on the right, we cannot find a linear line to separate the two groups, but it's possible we can find a nonlinear function, a nonlinear decision boundary that can separate the two groups. For example, we can just try to fit a nonlinear function instead of a linear function. Now, suppose you have already built your software for the hard margin formulation with linear function. How are we going to use that software and machinery to fit a nonlinear function? Well, we encountered this before. For example, how we extend a linear model. We have learned for linear model to nonlinear model. It's easy. We just add more columns in our design matrix. Add columns that reflect nonlinear features. For example, if we're fitting a quadratic function, we can just add quadratic terms. So that's and when we add more columns to the design matrix, it's the same as we enlarge the feature space from the original P to a higher dimension. So that's exactly what the nonlinear SVM is doing. We're going to embed our original p-dimensional feature vector x in a high-dimensional feature space, and then any linear function in the high-dimensional space actually corresponds to the nonlinear function in the low-dimensional or the original x space. Now, what's interesting is we don't even need to visit that high-dimensional feature space as long as we know how to compute inner product in that new feature space. So that's known as the kernel trick, and the nonlinear SVM often referred to as a kernel machine. So although the soft margin formulation and kernel machines are designed to address or handle non-separable data, but as you're going to find out, we can apply the same on separable data. After discussing this soft margin and kernel machines, and at the end, I will talk about some practical issues with SVM. Number one, as I mentioned before, in SVM, we just learn the decision boundary. So it's different from logistic regression or discriminant analysis. Here, there's no probability. We just find out the decision boundary. So once we learn the decision boundary, which is the solid blue line in those two pictures, we can just make our prediction. When a new test point is presented to us, we just decide is this point is from class 1 or -1 based on which side this point is located. And so we're going to talk about how we can go from binary decision boundary to probability outcomes, because sometimes it is appealing to have a probability instead of just 0 or 1 discrete decisions. And so far, we only talk about binary classifications. All SVM right now are formulated as a binary classification, and I'll discuss how we can move from binary to multi-class classification problems.